write the name of each of the following ions. Include Roman numerical where necessary. So barium here is shown to have a plus charge, so that's a barium ion. Ba is barium, and it's an ion because of the charge. This is zinc ion. In fact, this should be zinc 2 ion, but zinc only exists as one ion, so it's okay just to say zinc ion. There's no other oxidation number for zinc, so it's fine to just say zinc ion. Ion Fe can exist in two forms. You can have ion 2 or ion 3. So here you have to specify the oxidation number. This 3 is that 3. And then this is a perchlorate ion. This is what we use in bleach. You just have to memorize it. ClO4 negative. Perchlorate. Like if you have bleach, it's gonna be sodium perchlorate. That's a bleach. Okay, but this is the second part of the compound, so it's called perchlorate. Acetate. That's just how it's written. You just have to memorize C2H3O2 minus. Sometimes acetate is written as CH3COO minus. These are the same because you have 2 carbons, you have 3 hydrogens, 2 oxygens. Next, it's telling you to draw the dot structure. The dot structure of each of the following covalent molecules. What are their shapes and geometries? So dot structure, that means Lewis structures. The scientist that came up with this drawing is called Lewis structures. So again, like you did, the first step is to find the total valence electrons. Okay, so nitrogen is in the 5th column of the periodic table, so it has to have 5 valence electrons. You have 3 iodines. Each iodine brings 7 electrons because iodine is in the main group 7 of the periodic table. Remember how we counted the columns? You skip the value, then you continue counting the columns. Iodine, fluorine, chlorine are all in main group 7, so they have 7 valent electrons. You have 3 of them, so it's 21. You sum them up, is 26. First, like I told you, you have to look for symmetry. So I would put nitrogen in the middle, and then the iodines will go outside. Okay, I told you halogens and hydrogens will always be outside. So that's step number 1. And then after doing step number 1, you at least make a bond. A bond is made by 2 electrons. Each bond is 2 electrons. Okay, now going across the periodic table, electronegativity increases. Its electronegativity increases also going up the periodic table. So iodine is farthest to the right, so iodine is more electronegative than nitrogen. We have to satisfy the octet state rule for iodine. So just make sure each iodine has 8 electrons shared around it. If you count, those are 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. But we have 26 electrons to spread. The other 2 will go to nitrogen. So next you just draw the bonds, and of course these lone pair are unbonded, or those electrons are not bonded, so it stays like that. Show the bond between nitrogen and iodine like you did. If you are to find the geometry, again remember I taught you about valence shell electron pair repulsion theory. The electrons will repel, and this lone pair occupies a lot of volumes, like a big balloon, okay, compared to the bonds. So you expect repulsion. So then the iodines will not be on straight line like you drew. Instead, the iodine will go down because they are repelled by the lone pair which is up there. The bonds which have 2 electrons each are repelled. So to find the structure, molecular structure, you connect the atoms, you connect the elements. So like here, if I connect them, okay, I end up with a pyramid shape. So this molecule, similar to ammonia, has a trigonal pyramidal. Trigonal because down here you have a triangle. So it's trigonal pyramidal shape geometry. Okay. Just review on page 84. You see all those shapes. So if it was CH4, it's gonna take a tetrahedral shape. Bond angle 109.5 because of valence shell electron pair repulsion theory, VSEPR. Ammonia, because of the repulsion, again the bond angle will be roughly 107, or I would always say that you just take it as approximately 109.5, approximately 109.5. But here what's showing you is that if you have more electron pairs which are not forming a bond, you get the bond angle reduced. Okay, so we are going to continue to practice on the names of the ions. When you see CO3 2-, that's supposed to be a carbonate, like sodium carbonate, potassium carbonate. This is a phosphate. All these are called they are called polyatomic anions because there are several types of atoms. You have carbon, oxygen, phosphorus, oxygen, hydrogen, carbon, oxygen. So they are poly meaning many. Poly means many atoms, many atomic anions. You have many atoms making the anion. So this is called hydrogen carbonate. Of course, this is the carbonate part like we did here, and you have a hydrogen. This is what makes baking powder. Baking powder is sodium hydrogen carbonate. Alright, let's continue with shapes. Again here, that's an iodine, it's not an L. So you end up with this structure. Of course, first sum up your total valence electrons, and then create some symmetry where possible. Sometimes it's not possible to get symmetry, and then make at least a bond, and then satisfy the iodine before the carbon, because iodine is more electronegative than the carbon. You end up with this structure. So you did not finish to show the electrons. You need to show all those electrons whenever you're answering a question, because that's what you'll be looking for. In terms of shape, again, these bonds will repel. It's not 90 degrees as suggested. No. Because of the bonds will repel, two iodines will be on the plane. One will be away. We showed that bond to show away, the broken bond, and one will be towards. So like I showed you before, this is gonna give you a tetrahedral shape. If you connect all these atoms, you get a tetrahedral shape. So tetrahedral. Bond angle is approximately, for tetrahedral, bond angle is always approximately 109.5 degrees. Always for tetrahedral. Of course, bromine, you do the same thing. Find some symmetry. In this case, just a straight line. Make a bond and then satisfy the octet like you did. You added electrons, and the shape is linear because the BRs are sitting on a straight line. Krypton is an element of the periodic table, and krypton belongs to group 8 elements which are monoatomic. so they don't pair up. They don't, one Kr does not combine with another Kr like you did here in Br in Br2. Okay, so this should be Br2. In Br2, this is a halogen. Halogens are always diatomic. Okay, oxygen is diatomic, nitrogen is diatomic, hydrogen is diatomic, iodine is diatomic, but remember oxygen can be triatomic in ozone. Okay, so just these are few to memorize molecules. So cobalt dichloride, you have a metal cobalt and a non-metal chlorine. Whenever you react a metal with a non-metal, you know, I showed you the periodic table that has colors in it, how you can tell which side is the metals, which side is the non-metal, which side is a metalloid. Metalloids are neither metals or non-metals. So whenever you combine a metal and a non-metal, you get an ionic bond. What I'm saying is cobalt is a metal, chloride is a non-metal, the bond between should be ionic. Nitrogen always exists as N2. It does not exist as N by itself. So it's diatomic molecule. So it's a diatomic molecule. It's a gas. Gases are molecules. So if you can tell that something is a gas, yes, no, it's going to be a molecular element. Why is it an element? Because you have the same element. SO2 is a gas, sulfur dioxide. That's a gas. But this gas is made of two different elements, sulfur and oxygen. So it's a compound. So it's a molecular compound. It's a gas, so it's molecular. And then because it's made of different elements, so it's a compound. Potassium nitrate, like I said, whenever you combine a metal and a non-metal, metal plus non-metal, you're gonna get ionic compound. So that's why that's ionic compounds. Okay, again, remember nitrogen gas is made of the same element, so it's a molecular element. It's molecular because a gas. Sulfur dioxide is a gas, so it's molecular, but it's a molecular compound because you have two different elements in it. Let's see. Calculate the following: the number of CO2 molecules in 0.017 moles of CO2. So here you have to use Avogadro's number of particles. So this is how it goes. So 6.022 times 10 to the power 23 particles equals to 1 mole of particles. The question is, what are particles? Particles could be ions, particles could be atoms, particles could be molecules. So in this question, you are asked about the molecule. So we know that 6.022 times 10 to the power 23 number of particles. In fact, let me use the number of molecules because that's what the question involves. The particles we are talking about are molecules. Molecules should be equal to 1 mole, but you are given 0.0170 moles of CO2. So the Avogadro number of CO2 molecules should be equal to 1 mole of CO2. So if you want to get this answer here, how many molecules will you have in 0.017 moles of CO2? Simply cross multiply. So that will be 0.0. you multiply it by the Avogadro's number, and then we are dividing by 1 mole. So this and this will go. If you multiply, you get 1.023 times 10 to the power 23. I hope you did the math right. I've not used my calculator, but just check your math. Okay, next. Gasoline is a fuel containing ethanol. So that's the formula for gasoline, that burns in oxygen to give CO2 and water. So write the balanced equation. Write the balanced equation for this reaction. So I think what you need to do is to balance. I usually start by balancing the metal, in this case the first element, so carbon. There are 2 to the right, so you put 2 here to make 2 carbons. Then you have 1 oxygen, and then you have 6 hydrogens. So to balance the 6 hydrogens, you put 3 before the hydrogen of water, so you get 3 times 2 is 6. Now you have 4 oxygens here, you have 3 oxygens here. To your right you have 7 oxygens. To your left it's 6 and 1, you have 7 oxygens. So everything is balanced. What type of reaction is this? Of course it's combustion, because you're simply burning in oxygen. How many moles of oxygen are needed to react completely? So the point is completely, with 8 mole of that compound. So you know 8 mole of that. So 3 moles of oxygen react with 1 mole of gasoline. So this should be 6. That should be 6 C2. So you see the reacting ratio in your equation. 3 of oxygens react with 1 of gasoline. So the reacting ratio is 3 to 1. And because you want the answer to be moles of oxygen, so the moles of oxygen will be on top. 3 moles of oxygen react with 1 mole of gasoline. Gasoline will be at the bottom, so that this will cancel with that. So if you multiply the numbers, the answer will be in moles of oxygen, and that's 24. So that's correct. The burning of 125 grams of ethanol will theoretically produce 147 grams. So theoretical yield means if nothing goes wrong, you should get, if no errors, if nothing goes wrong, you should get 147 grams of water. So if 73.5 grams of water actually produced, what's the percent yield? So 73.5 is actually what you got from the experiment, so it's called actual. Like I said, theoretical yield is what's expected to be found, to be obtained if nothing goes wrong in the experiment. So the formula is percentage yield is actual, what you got in the lab, over what you expected to get times 100. That turns out to be 50% yield. How many moles are there in 4 grams of water? So the first thing that you do again is to find the formula weight. Use the periodic table to read the mass of your elements, not the atomic number, the mass. The most common mistake students do is to use the atomic number to find the mass. The atomic mass is usually the big number in the box in the periodic table. So oxygen has atomic number 8, but it has mass number 16. Hydrogen has mass number 1, but you have 2 of them. You sum, you get 18 grams. 18 grams per mole. So 1 mole of water should weigh 18 grams. So if 1 mole H2O has a mass of 18.02 grams. That's what gram per mole means, gram per mole. So if 1 mole has 18 grams, you're asking yourself, what about 4 grams? The question says 4 grams, not 40. So what about 4 grams? So again, very simple, cross multiply. So your expression will be 4 grams times 1 mole H2O divided by 18.02 grams. So this and these grams will go, you're left with moles. So you need to do your math. 18.02 should give you the number of moles. You have to write the number of moles using your calculator right there. Okay, here you need to determine the type of reactions that are going on. Is it displacement? Is it combination? Is it double replacement or combustion? So let's start here. I think the equation is balanced. You see an exchange. So you have A, B, C, D. So copper is your A, oxygen is your B, hydrogen is your C, chlorine is your D. So now your A ends up with D, which is chlorine, and then your hydrogen, which was C, ending up with B. So you see, they have exchanged. It's like two couples exchanging their wives and husbands. So it's double replacement. You're replacing groups on all the reactants, so it's double replacement. A, B changes to AD, CD changes to CB, so it's double replacement. There's another one that's called single replacement. We'll look at it shortly. And then here you have two things making one thing, so you're combining, so it's combination. Here you are using oxygen to give CO2, so it's combustion. You're burning an organic compound. Here you have, again, what's this? This is barium. I don't see. Let's see. This should be barium carbonate, potassium chloride. Yeah. So this should be barium chloride. So again, you have A, B, potassium is C, carbonate is a polyatomic anion, so it's D. Turns out to be, the product will be AD, polyatomic anion, barium carbonate, potassium was C, the chloride was B. So ADCB from ABCD. So it's double replacement, just like we did there. Okay? Type of reaction, chapter 4. So let's do some practice with this. Here you have two things combining to give you one thing. So obviously this is combination. That's combination reaction. Here you have, let's see what you have. You have A, which is just a bromine. Lithium, let's take lithium to be B. Let's take iodine to be C. Let me change the colors. So you end up with A combining with B, and then you have C by itself. So it simply means a boyfriend came and broke up this marriage. So the husband in this marriage will be displaced and become single, right? So A took B and C displaced. Bromine reacted with lithium, iodine is displaced. So this is called single replacement. Okay? Because this guy right now is single. It's not paired. Here you have aluminium reacting with ion 2 nitrate. Again, you have group A. So this is polyatomic anion, so I'm gonna say C. Okay, so A and C are combined. Okay, A and C are combined. B is displaced and it's single by itself. So again, this is single replacement reaction. Here, magnesium will be our A, oxygen will be our B, hydrogen will be our C, chlorine will be our D. You end up with A and D combined, and you end up with C and B combined. Obviously, there's an exchange of husband and wife, both sides. So this is called double replacement. Complete exchange. Here, you have one thing broken apart to give you two things. Sometimes it's two or more. So because it broke apart, it fragmented to give you water, hydrogen peroxide breaks down to give you water and oxygen. This one is called decomposition. It decomposed, it broke down. So this is a decomposition reaction. Okay. Here you have a polyatomic anion, let's call it A, and another polyatomic anion, let's call it B. Strontium is an element C. Hydroxide is a polyatomic anion, let's call it D. So you end up with C and B combined and end up with A and D combined. So again, this is a complete exchange. You should call it double replacement. Okay, here I'll call my hydrogens A, the sulfate polyatomic anion B, sodium I'll call it C, OH I'll call it D. So you end up with you end up with C combining with B and A combining with part of the oxygen, which I might call D. Okay, so again, this is double displacement or double replacement. So here, obviously, A, B, and C are reacting. So you end up with A, C, nitrate is a polyatomic anion, displacing B. So this is singled out. So this is single replacement reaction. Okay. Here you have A, copper, B, polyatomic anion, potassium is C, chloride is D. It ends up combining to give you C, B, and A, D. So again, another double replacement reaction. So this is how you characterize whether a reaction is combination, single replacement, double replacement, or decomposition. Okay, so let's do the next one. Name the following. Now, boron is in main group 3 and it should be a metal. So let's say that boron will have 3+. Chlorine is main group 7, so it's missing one electron to be stable, so it will be a negative. So to find the formula, you see boron will have a 3, chloride will have a 1, but because you have 3 chlorines, we're going to call it boron trichloride. You don't need to say boron 3 trichloride, because boron has no other oxidation number other than 3. And then B, of course, you have 1 sulfur and 6 halogens. So the first part of the name will be sulfur, not sulfide, because that's the first part of the name. If sulfur was on the right, we'll call it sulfide. But because it's on the left at the beginning of the formula, we'll call it just sulfur. But fluorine is not going to be called fluorine, it's going to be called fluoride because it's on the left of the formula. But there are 6 of them, so it needs to be sulfur hexafluoride because there are 6 fluorines. And then of course we did the formula of acetate, and I think you wrote it wrongly. You were supposed to have 3 hydrogens and 2 oxygens. So we say the acetate is CH2, CH3, O2 minus, and then you have a hydrogen. So the complete name for this will be hydrogen acetate. There's an acetate in that formula, which is this part. And then D, you have a calcium and fluorine. So again, if you take this number back and you take the 1 here back, you get Ca2 plus and F minus. Calcium has only 1 oxidation number of 2. Okay, group 1, group 2 elements, group 3, main group 3 elements have 1 oxidation number. Always have 1 oxidation number. So calcium will have its 2 plus, it's in the main group 2. So this is calcium fluoride. You don't need to say difluoride, it's just calcium fluoride. So you're missing an O on your answer. So, fluoride. Next, E, you have ion combined with a polyatomic anion, which is NO2. Notice that these 3 should go back to the ion, and the one that's here will go up on the polyatomic anion. So you get F3 plus and you get NO2 minus 1. We don't say minus 1, we just say minus. Anyway, ion can exist as ion 3 or ion 2. So in this case, you have to specify the Roman oxidation number. So the answer will be ion 3, and then this polyatomic anion is a nitrite, not nitrate. Nitrate is NO3 minus. This is NO2 minus, so it's nitrite. This guy is nitrate. Give the chemical formula of the following. Okay, so calcium has a charge of 2 plus. Cyanide is Cn has a charge of minus. So this number comes down, this number comes down. So the formula is Ca. Cn is polyatomic anion, so we have to put the 2 outside. Calcium cyanide. And then potassium oxide. Potassium has a charge of plus. Oxygen usually has a charge of 2 minus because the oxygen needs to gain 2 electrons to be stable. Okay, potassium needs to lose 1 electron to be stable. That's why it's a plus. These 2 will go down, the 1 will go down. So you end up with K2O. We don't put 1 there. We just write it as K2O as a formula. Lead carbonate. So that's Pb. We know carbonate is CH CO3. Pb has charge of 2 plus. Carbonate has a charge of 2 minus. So in other words, you should have dropped these numbers down here. So you should end up with Pb2 CO3 2. But these 2 are the same. Those 2's are the same. So we don't need to write them down there because they will cancel out. So the formula will be lead CO3. We don't need to put brackets and put 1 because it's just a ratio of 1 to 1. D, tin 4 sulfate. So it means our tin will have a charge of 4 plus. That's why it's called tin 4. Lead 2 has a charge of 2 plus. Tin 4 has a charge of 4 plus. Sulfate is written like that. You have to know the formula for sulfate, like I said before, for you to get the right formula. Okay, so you drop the 2, you drop the 4. So you end up with tin 2 polyatomic anion with a 4 on there, like we did before. So 4 there. Like we did before, we have to find the whole number ratio of the subscript. So the answer will be Sn, which is for tin. Tin is Sn. Sn SO4. 2. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 is there. Okay. Beryllium fluoride. This is just additional question. Beryllium is main group 2. It's a metal. Fluorine is group 7. It needs 1 electron to be stable. Beryllium needs to lose 2 electrons to be stable. Okay, so you end up with BeF2, which means beryllium fluoride will be BeBr2 because bromine again is -1. You drop. Calcium iodide. Calcium is a metal group 2. Iodide, 1 step to be noble, stable. So drop the 1. Calcium iodide will be calcium I2. Aluminium fluoride. Aluminium is main group 3. It's a metal, so it's 3 plus. Fluoride is halogen group 7. 1 step to be group 8. So you drop. So you get Al1F3. Copper 2 sulfate. So copper 2 plus, a sulfate is 2 minus. If you drop these 2, the other 2 on the polyatomic anion, you get this. Of course, like I said, you can get a whole number. You get CuSO4. Magnesium hydroxide. Magnesium is group 2. Hydroxide has a negative charge. Is a polyatomic anion. You drop the 2, you drop the 1, you get MgOH, polyatomic anion gets the 2. That's magnesium hydroxide. Okay. So which of the following have dipole effect? I told you, you have to determine, use your periodic table and tell yourself electronegativity increases across the periodic table and upwards the periodic table. So oxygen is more electronegative than carbon. We use the slashed arrows to point the more electronegative element. In this case, they cancel because they are on straight line. So you have dipole moments, yes, but they do cancel. So overall, the molecule is nonpolar. It has dipole moments per bond, but they cancel. So the molecule is nonpolar, no net dipole moment. Like I told you, this formula will be taking a tetrahedral shape. The chlorines are not on straight line because of repulsion. So this guy is tetrahedral. Chlorine is more electronegative than carbon. So you have dipole moments at an angle. Okay, 109.5. So they don't cancel. So this molecule is polar. Okay. So here, carbon and hydrogen, they don't have much electronegativity difference according to Pauling scale. So this bond is nonpolar, which means all these bonds are nonpolar. So the whole molecule is nonpolar. So if the whole molecule is nonpolar, there is no dipole forces. Okay, so next let's see which of the following are capable of hydrogen bonding. I told you if you want to know if a molecule can hydrogen bond, you look for hydrogens bonded directly to an electronegative element like oxygen. So oxygen is electronegative. So you expect that this hydrogen will be partially positive because the dipole moments are stealing electrons from hydrogen to oxygen. Electrons are negatively charged. So this hydrogen is bonded to an electronegative element, but these hydrogens on carbons, they are not bonded to an electronegative element. I do not expect hydrogen bonding to happen here. For hydrogen bonding to happen, both molecules should have hydrogens which are bonded to electronegative element. This structure here does not have hydrogens bonded directly to a strong electronegative element, so there's no hydrogen bonding. Same applies here. No hydrogen bonding possible because the structure on top has no hydrogen bonded to electronegative element. The structure on the bottom has no hydrogen bonded directly to electronegative element. So again, I don't expect in between here to have hydrogen bonding. So no hydrogen bonding. But when you look at these structures, it's possible because nitrogen is electronegative. So you have a partially positive hydrogen here. If you bring another ammonia to get close together, because nitrogen takes electrons towards itself, is electronegative, it's going to be partially negative. So which means for a second molecule, the nitrogen will be partially negative, the hydrogen will be partially positive, because these hydrogens are bonded to an electronegative element. So I would expect this hydrogen right here to hydrogen bond with the nitrogen of the second molecule. So yes, there is hydrogen bonding between two molecules of ammonia. Okay, so this nitrogen will bond with the hydrogen of the second molecule by hydrogen bonding. Here oxygen is electronegative, so hydrogen will be partially positive because of dipole moments. Okay, nitrogen will be partially negative because of dipole moments. So if you bring ammonia close to a molecule of water, you expect to have hydrogen bonding between the two molecules because both molecules have hydrogens bonded directly to an electronegative element. Here nitrogen is electronegative element, here oxygen is electronegative element. So acetic acid, this is acetic acid or the component in vinegar. So again you have hydrogen bonded to an electronegative element. That hydrogen is partially positive, and of course I told you the oxygen will be partially negative because of dipole moments. Okay, so hydrogen bonded to an electronegative element oxygen, hydrogen bonded to an electronegative element oxygen. If you bring these two molecules together, the hydrogen of the electron of the first molecule will get attracted to the oxygen of the second molecule, and that's how you get hydrogen bonding. So in summary, you have to look for hydrogens bonded to electronegative elements and then bring the two molecules together. They should do hydrogen bonding between themselves. Which of the following are capable of hydrogen bonding? This one will not do hydrogen bonding because no hydrogen is bonded to here. No hydrogen is bonded to an electronegative element. These hydrogens are bonded to carbon, so I don't expect two of these molecules to make hydrogen bonding. Same thing here, I don't expect two of these molecules to do hydrogen bonding because the hydrogens are not bonded to an electronegative element. Carbon is not very electronegative. But here, hydrogen peroxide, if I bring another molecule of hydrogen peroxide, I expect hydrogen bonding to happen because of dipole moments. Here, hydrogen is positively charged, oxygen is partially negative, which means for the second molecule will be the same, oxygen will be partially negative, opposite charges attract, I'm able to do H bonding between these two molecules of hydrogen peroxide. Okay, so the question here is which of the following are capable of dipole moments? Again, I point towards the oxygen. So because oxygen is more electronegative than the carbons, here you have carbons in between. So carbon will be partially positive, oxygen will be partially negative. So which means this will be partially negative, this will be partially positive. Now because you have these partial charges and it's between elements that are not hydrogens, we call that dipole-dipole. So acetone, which is nail polish remover, this guy is acetone, you don't need to know that, but anyway, you just look at the structure and judge if two of the molecules of acetone will do dipole-dipole. So these two molecules can do dipole-dipole as the question asks here. I modified to ask you for dipole-dipole. But here there is no electronegativity, there's no dipole moment, so you don't expect dipole moments between these two molecules. And because there's no also hydrogen bonding possible, the only other option you have here is very weak. We call the forces that will be in between very weak London forces, London dispersion forces. So for these two molecules right here, there's no dipole moments, which means there's no hydrogen bonding possible. There's no dipole-dipole like we have in B. So the only option you have is London dispersive forces. So again, this is not an answer for our question because our question is looking for two molecules that can do dipole-dipole. B is the answer, this dipole-dipole. A only has London dispersive. For C, like I said, hydrogen is bonded to electronegative element, oxygen, so oxygen will be partially negative, hydrogen will be partially positive, hydrogen partially positive, oxygen partially negative. So between this molecule, methanol, and water, I expect between these two molecules to have hydrogen bonding. So this is not the answer according to this question. The two molecules capable of doing dipole-dipole is only B. C will do hydrogen bonding, A will do London dispersion forces. Okay. When the gases dihydrogen sulfide and oxygen react, they form the gas sulfur dioxide and steam. So this is steam. This is supposed to be G, not aqueous, because steam is a gas. Write a balanced equation. So I think you do by inspection. You first try to balance your hydrogens and then balance your sulfur. Or you can start by balancing your oxygen and finish the other way around. I see what you did. You tried to balance the oxygen by putting 3/2, so that here you'll have 3 oxygens and this side you'll have 3 oxygens. But by rule, in balancing equations, you don't want fractions, so you multiply everything by 2. So you multiply this equation by 2, and that's how you got this to get rid of the fraction 3/2. And turns out this is balanced because you have 2 sulfurs, 4 hydrogens, 6 oxygens. Of course, you have 4 plus 2 oxygens, so 6 oxygens. How many grams of oxygens are needed to react with 2.5 grams of dihydrogen sulfide? So the reacting ratio is 2 to 3, 2 to 2. So here we are looking for grams of oxygens that gives you dihydrogen sulfide. Okay, so here you are looking for grams of oxygen that are needed to react with dihydrogen sulfide. So we are paying attention on this ratio, 3 to 2. So 3 moles of oxygen will react with 2 moles of hydrogen dihydrogen sulfide. So in this case, if you want to do the conversion, the first thing you want to do is to convert your dihydrogen sulfide to moles, and then use the moles, react with the converting factor, and then multiply by the formula weight of oxygen to get the mass of oxygen. So that's too much to say, but let's do it stepwise. So let's convert the dihydrogen sulfide, the mass of dihydrogen sulfide, to moles. Obviously, the formula for moles is equal to given mass over formula weight or unit weight. So 2.5 grams divided by formula weight of dihydrogen sulfide is 39.5 grams. Okay, this should give you moles. But the other way to do it is this way. This is the best way to do it actually. So you will tell yourself, I like using reacting ratio. You tell yourself 1 mole of dihydrogen sulfide is equivalent to 39.08 grams. So what about 2.5 grams of dihydrogen sulfide? So you cross multiply, you will get your expression to be 2.5 grams dihydrogen sulfide multiplied by 1 mole dihydrogen sulfide divided by 39.08 grams dihydrogen sulfide will give you the number of moles. Okay, so this will give you the number of moles of dihydrogen sulfide. That's the first part of your reaction. So but your dihydrogen sulfide reacts with oxygen in a ratio of 3 to 2. So those moles are multiplied. The moles that you get up here is what you get where the line is. They are multiplied by the conversion factor. 3 moles of oxygen reacts with 2 moles of dihydrogen sulfide. So that's why you have this expression here, 3 over 2. And it's written like this and not the other way around because you want this to cancel out with that, so you'll be left with moles of oxygen. So that will put you here, you get moles of oxygen. And then multiply by the formula weight of oxygen, you get the mass or the weight of oxygen needed to react with dihydrogen sulfide. Okay? So this is how you can set up your equation to get the moles of oxygen. Okay, so calculate the mass of iron required to produce 4.5 grams of silver given the following equation. So again, reacting ratio is 1 to 1 to 1 to 1. That's not correct because it's not balanced, so you have to balance all these guys to get the right ratios, reacting ratio coefficients. So it's 1 mole of iron reacts with 3 moles of silver nitrate to give you 1 mole of iron nitrate and 3 moles of silver. So the first step is to find the moles of silver. Of course, you tell yourself 1 mole of silver is equivalent to 107.8 grams. So what about 4.55 grams? You cross multiply, you'll get this equation. So those are the moles of silver. So those moles of silver, okay, are formed from 3 moles of silver are formed from 1 mole of iron. We need to find the mass of iron. So to find the mass of iron, we have to find the moles of iron before we find the mass of iron. So the reacting ratio of iron to silver is 1 to 3. So we use our conversion factor to find the moles of iron. So we already found the moles of silver. We know that 3 silvers are made from 1 iron. So we use our conversion factor. You have to set it up this way, not the other way around, because you want the moles of silver to cancel out and you'll be left with the moles of iron in your answer, moles of iron. So now that you have the moles of iron, convert the moles to mass. You will tell yourself 1 mole of iron has a mass of 55.85 grams. So what about 0.0141 moles of iron? Cross multiply, you get this expression. You'll get the mass of iron required that the question wants. Okay?